Good afternoon, students. Welcome for the physics class. Okay, so in the last hour, we have discussed about the combination of resistors. We have seen how to combine the resistors in a series manner and how to combine the resistors in the parallel manner. And also, we have obtained the expressions for series combination of resistance and parallel combination of resistance. After that, we have gone through one more topic, that is cells. We have studied about the devices in the electrical circuit that are called as cells. We have given the expressions for EMF of the cell, terminal potential difference, internal resistance of the cells, and we have discussed all those quantities in detail. And after that, we have also gone through cells in a parallel manner and cells in a series manner. Means how we have discussed the combination of resistors, in the same way we have discussed the combination of cells also. You know how were the cells? They are having two terminals, positive terminal and negative terminal. To combine them in series, we have connected them one negative terminal to the another positive terminal, another negative terminal to the another positive terminal. Like that we have combined them in series. So how we got the series combination? So in the series combination, we have also gone through the expressions for the current. So we have got expression for the current I in the series combination of cells as N into E divided by N into R plus capital R, where this NR is a effective internal resistance and this is the effective EMF and R was the external resistance. Similarly, for the parallel combination of cells also, we have got the expression for I, that was M into E divided by R plus M into R. This we have discussed in the last class. Okay, here we have to know one important thing about the combination of cells in a parallel way and cells in a series way. That is, you can take it as a note also. So what is the important note about series combination and parallel combination of the cells is, when cells are connected in series, when cells are connected in series, they can give you maximum current when you are having R with a maximum value. Means the first note is what? When cells are connected in series, they will give you maximum amount of current, large amount of current when you are providing a large external resistance over there. When you are providing a small external resistance, means if R is very much small than the internal resistance, there you will not get any maximum current in the series combination. So first thing is what? In a series combination, you will get a maximum amount of current when you are providing one large external resistance. In the same way, so in the parallel manner, if you want to get the maximum amount of current, there you have to provide small external resistance. Means R should be small than NR. So when R external resistance is very much small than the internal resistance, there you will get the maximum current in the parallel combination. In the reverse manner, in the series combination, you will get a high current with a high external resistance. In the parallel combination of cells, you will get high current with a small external resistance. This is the important thing you have to know about the currents in the combination of cells. So, all those things about cells we have studied in detail in our last classes. So, today I am going to discuss one more new law which comes in current electricity. That is, you have studied about Ohm's law in your last classes, okay, and you have applied Ohm's law to so many circuits also. You know thoroughly about Ohm's law, okay. So when you are applying Ohm's law to any circuits, those circuits were simple. That means what? You were applying the Ohm's law for the simple circuits. So when you are coming in contact with the complicated circuits, at that time you cannot use Ohm's law over there. So what happens when you come in contact with the complicated electrical circuits? So at that time you have to use one more important law which comes in current electricity, that is Kirchhoff's laws. So these are the important laws which are coming in the electrical circuits. You have studied Ohm's law for the simple circuits, but when you are dealing with the complicated circuits, you have to go through Kirchhoff's laws. Okay, so these are the laws which comes in the current electricity, in which we are dealing with the current and voltages. In the Ohm's law also we have discussed with the V is equal to IR, that is voltage, current and resistance. Here also we are discussing about voltage and current, but in a complicated electrical circuits. You are applying the laws of voltage and laws of current in the complicated electric circuits. So when this Kirchhoff's laws came into existence, so the German physicist Gustav Kirchhoff was the one who described about Kirchhoff's laws in the year 1845. So he explained the Kirchhoff's laws to deal with the current and voltage, in the electrical circuits. For that purpose, he explained Kirchhoff's laws, or also you can you say it as a Kirchhoff's rules. Okay. So before going to the Kirchhoff's laws, you have to know about three important definitions. Means in order to understand the Kirchhoff's laws in a simple way, you have to deal with the three important definitions. So first is electrical circuit. What is electric circuit, that you have to know before going to the statements of Kirchhoff's laws. And you have to know what do you mean by node or junction. And also you have to know about what do you mean by loop or mesh. So these three definitions you have to be perfect when you are dealing with the Kirchhoff's laws. Okay, so electrical circuit means, so far in this chapter you have come across several electrical circuit. Let's consider a simple electrical circuit which we are discussed in the last class only. So here you are having R, and you are having a cell over here, and like this anything. One resistor is connected to the one cell. Okay, so this is an electrical circuit. Or else you can consider, in the first classes only we have considered one conductor in which electrons are moving. For that we have applied the potential difference by the battery. So this is also an electrical circuit. So in your PUC classes also, while doing the labs, you have came across some electrical circuits. So when you imagine electrical circuit, you will get some components over there. Means resistors will be there, ammeter will be there, voltmeter will be there, capacitance, inductance, so many things will be there. So how we can define electric circuit? Means electric circuit is one combination. Electrical circuit diagrams will be there, na? You are drawing in your journals or in your manuals, you may say them. So electrical circuit is nothing but what? It is one combination. Combination of what? Combination of circuit elements. Combination of circuit elements or electrical sources. This battery or cell were the electrical sources which will provide the electricity to this current. So we can define electrical circuit as it is a combination of circuit elements or electrical sources connected in a complicated manner. Means there so many things were connected, na? So we can feel it complicated. That's why we can define it as the electrical circuit is a combination of circuit elements or electrical sources connected in a complicated manner. So this was electrical circuit. Okay, so in electrical circuit you will get node or junction. That means what? In electrical circuit you will get a point over there, a point at which two or more conductors meet. In the last class only we have studied about parallel combination, na? So how we have drawn there? So we have drawn it like this. One cell was there, we have drawn them like this, na? Parallel combination of resistors like this. Simply roughly I am drawing. So this is a point where four resistors are meeting, yes or no? So this point we can call it as a node or junction. Means a point in an electrical circuit where two or more conductors are meeting is called as a node or junction. It is a point in an electrical circuit where two or more conductors are meeting. Okay. So next is loop or mesh. So whenever you saw an electrical circuit, when that electrical circuit is completely closed, means one full path will be covered na. It is a closed path in an electrical circuit. Loop or mesh is nothing but what? A closed path in an electrical circuit. Any electrical circuit if you consider, they will be closed completely. One battery will be there. From the positive terminal of the battery, you will be going with the so many sources, and that will end at the negative terminal of the battery. So that is what one closed path will be there. That closed path in an electrical circuit is called as a loop or mesh. Okay, the combination of various circuit elements or electrical sources connected in a complicated manner is called as electrical circuit. The point in an electrical circuit at which two or more conductors are meeting is called as node or junction, and a closed path in an electrical circuit is called as a loop or mesh. So before going to the explanation of Kirchhoff's laws, you have to be aware about these three definitions. Okay. So when you are going to deal with the Kirchhoff's laws, totally there are two Kirchhoff laws. So Kirchhoff's first law and Kirchhoff's second law. You have two laws or two rules which are given by the scientist Gustav Kirchhoff. There are two laws, Kirchhoff's first law, Kirchhoff's second law. For the Kirchhoff's first law, you can also tell it as a junction law. What is junction? You know already. So for the Kirchhoff's first law, you can also give a name as junction law or Kirchhoff's current law. Or also you can call it as a Kirchhoff's current law. So let's discuss about Kirchhoff's first law, which is also called as junction law or Kirchhoff's current law. Briefly, in a short form, you can also call it as a KCL, Kirchhoff's current law. Kirchhoff's current law or Kirchhoff's junction law or Kirchhoff's first law. Okay. So what is the statement of KCL? Kirchhoff's current law, Kirchhoff's first law. The statement of the Kirchhoff's law is like the algebraic sum of all the currents meeting at a node is 0. The algebraic sum of all the currents meeting at a node is 0. So the Kirchhoff's law states that algebraic sum of the currents meeting at a node in an electrical circuit is 0. What is node? You already know. Or what is junction? You already know. Means it is a point in an electrical circuit where two or more conductors are meeting. So in order to explain the Kirchhoff's first law, I'll consider O as a node or junction in an electrical circuit. So O is a junction or node in an electrical circuit. So at this point in an electrical circuit, so many conductors are meeting. Like now I will consider first conductor with a current I1. So I1 is the first conductor entering the point O. Let's consider I2, which is leaving the point O. Similarly, consider I3, which is leaving the point. You can see the directions here. This is I1 is entering, I2 is leaving, I3 is leaving, and I4 is entering the point O. Okay, so I1 is a current which is entering the point O, I2 is a current which is leaving the point O, I3 is also a current which is leaving the point O, and I4 is the current which is entering. And consider one more thing, I5 which is entering. So totally you are having 5 currents over there. So what the law states, the algebraic sum of all the currents meeting at a point is 0. So for the first you consider I1. I1 is entering. So take it as a I1 plus I2. I2 is a leaving. So take it as a negative minus I2 because it is leaving the point. Third, I3. It is also leaving. Fourth, I4 entering plus I4, and the fifth entering plus I5 equal to what we have to take? 0, because the algebraic sum of all the currents meeting at a point O is equal to 0. This only was the statement of Kirchhoff's current law. Okay, so how can we write it further? I1 minus I2 minus I3 plus I4 plus I5 equal to 0, or also you can write it like I1 plus I4 plus I5 equal to I2. This minus I am taking to the opposite side, and plus I3. So we can write it like this. Okay, so this we can write by the Kirchhoff's current law. This states that the algebraic sum of all the currents meeting at this point is 0. So you can see here I1, I4 and I5. I1, I4 and I5 were the currents which are entering the point O, and I2 and I3 were the currents which are leaving the point O. So by this what we can conclude, the currents which are entering the point O are taken as positive, isn't it? And the currents which are leaving the point O are taken as negative. This is the first thing which you are concluding by the KCL. You are concluding that the currents which are entering the node are taken as positive, and the currents which are leaving the node are taken as negative. This is the first thing you are taking. And second, I1 plus I4 plus I5 is equal to I2 plus I3. Means the sum of currents entering is equal to sum of currents leaving. Means how many amount of current is coming into the point, the same amount will be the leaving. So this we can say it as a conservation of charge. The second thing which you are concluding from the Kirchhoff's first law is, Kirchhoff's first law signifies about conservation of charges. Okay, so these 2 points we are concluding by using Kirchhoff's first law, which is also called as Kirchhoff's current law. Okay, similarly, let's go for the next thing, which is Kirchhoff's second law. Okay, so let's go for Kirchhoff's second law, which is also called as a loop law or Kirchhoff's voltage law. Kirchhoff's first law was called as Kirchhoff's current law. Second is called as Kirchhoff's voltage law or loop law. Okay, so what it states? What it states? What is the statement of Kirchhoff's second law? Means it states that the algebraic sum of EMFs, the algebraic sum of EMFs is equal to the algebraic sum of IR products. The algebraic sum of EMFs in a closed loop is equal to the algebraic sum of IR products at different parts of the electrical circuit. So how can we state it? In a current loop, Loop means a closed path, a closed electrical circuit. In a current loop, the algebraic sum of EMFs is equal to the algebraic sum of IR products at various parts of that electrical circuit. IR products is nothing but what? By Ohm's law you know, V is equal to IR. So you can also write it as sigma E is equal to sigma V, total V. V is nothing but voltage. So instead of that only I am taking IR. The algebraic sum of EMFs in a current loop is equal to the algebraic sum of IR products in a different part of electrical circuit. So how can we prove this means? So for this you have to consider a closed loop, means a closed path in an electrical circuit you have to consider. So I just consider a simple electrical circuit which is closed. So for that we'll consider, let's consider 3 points A, B, C. You can imagine this is a part of one circuit, means from A also circuit is continued, from B also circuit is continued, and C also circuit is continued. Means in one complicated circuit, ABC is just a part. ABC is just a closed path. It is one loop. Okay. So here I'll consider from the point B to A, I am considering one current. And here one cell, and the current is I2. I2 is a current which is coming from B to A, and here I am having one cell and one resistor. So with respect to I2, let's call this as R2 and let's call this as E2, because this is one cell with the EMF E, and with respect to the current I2 I am giving it a name I2, E2. Okay. Similarly, from the point C I am having one more current coming across. So for this we will call it as a I1. With respect to I1, what we have here? We have here E1, a cell with the EMF E, with corresponding to I1 it is E1, and the resistance R1. Similarly, from the point C to B, I am having one resistance, one current coming across, that is I3, and corresponding to that R3. So this is A, B, C is a closed loop in an electrical circuit. Okay. So here while dealing with the KVL, we have to follow the direction. You can also direct clockwise direction, or you can go by anti-clockwise direction. You have to traverse in any of the direction. Traverse means what? You have to move in any of the direction. So for first time I will move in a clockwise direction, means I am traversing in a clockwise direction. So I am going from A to C, C to B, B to A. Okay. So when you are moving, if the current is in the direction of traverse, means you are moving in this way and current is also in this way, you have to take the current as a positive. These are the sign conventions. But when you are moving in this way and current is moving in an opposite way, you have to take current as a negative. The first sign convention is what? The current direction, if it is moving in the direction of traverse, it is positive. If it is moving in a direction opposite to traverse, it is negative. Current is positive in the direction of traverse, current is negative in opposite direction of traverse. This is the first convention. And EMFs you are having over here, cells you are having, when the cell is moving from negative terminal to positive terminal, means from negative to positive, then it is plus E. You have to take the EMF as plus E, but when it is traveling from positive to negative, you have to take it as minus E. So totally we are having two conventions. Okay, two sign conventions. By using them only we are traversing in this circuit. Okay, so let's start in a clockwise direction. Okay, let's move like this. Direction is like this. Let's move like this. Here we are having I1, R1 we are having. Okay, but the direction of I1 is opposite for the direction of traverse. Like for that I'll take minus I1 R1. So in this part of the loop we are having minus I1 R1 because the current is moving in a direction opposite to the traverse. Okay, next move here now. You are moving like this only, traverse is like this only, current is also in the same direction. So for that you consider plus I3 R3. Okay, so next from B to A, you are moving like this and current is also moving like this. So obviously plus I2 R2. So this is what algebraic sum of IR products. So that will be equal to what? Algebraic sum of EMFs. So what will be the algebraic sum of EMFs? Again start moving like this, positive to negative. Here EMF is what? Positive to negative. So if it is positive to negative, we have to take it as a minus. So it is a minus E1. Okay, and come here. Here we don't have any EMFs. In the next part we have EMF which is moving from negative to positive. This EMF is moving from negative to positive. That's why it is taken as positive. So it is plus E2. Understood how to traverse in the closed loop? We are traversing in the clockwise direction and we are moving like this. So it is opposite here. That's why we are taking minus I1 R1 plus I3 R3 plus I2 R2. Again with respect to the EMFs, positive to negative, negative minus E1 and negative to positive, positive plus E2. Okay, so you can also write it as now I2 plus I2 R2 plus I3 R3 minus I1 R1. Okay, and E2 minus E1. You can change the signs like this also. So this is how we are dealing with the Kirchhoff's voltage law. Understood? Also, if you move in an anti-clockwise direction, so what if you move in anti-clockwise direction? The same things you will get, only with the different signs. So here we are getting I2 R2 plus I3 R3 minus I1 R1. So when you move in an anti-clockwise direction, you will get minus I2 R2 minus I3 R3 plus I1 R1. Since it is an anti-clockwise direction, and minus I2 plus E1, minus I2 plus E1. So this is the way how to deal with the Kirchhoff's voltage law. Okay. So these are the very important laws in the chapter current electricity. When you are dealing with the complex circuits, you have to deal with the Kirchhoff's laws. Okay, you are solving some examples also on the Kirchhoff's laws, and the problems on Kirchhoff's laws are very important. In order for your simple understanding about Kirchhoff's laws, I will take just a simple example for each law. Like for the Kirchhoff's current law, I am drawing a diagram over here. Just consider this as one small exercise. So 2 ampere. One current is there, that is 2 ampere. One more current is meeting at this node, 2 ampere. I hope you are good in understanding of node and junction. Before going to the laws only, I told 1 ampere. Here I am drawing the currents because Kirchhoff's first law deals with the currents only. Here one more partition I have, one more current, 1.3 ampere, and at the last the current I is moving. Okay, so for this particular node, for this particular circuital diagram, let apply Kirchhoff's current law. Kirchhoff's current law is the algebraic sum of currents meeting at a node is always 0. Okay, so for this node, the current 2A is entering. The current 2A is entering. So if they are entering, you have to take them as positive. Okay, so 2 plus 2. Okay, next go forward. So here also you got one node over there. So for that node, what is there? 1 ampere is leaving. So if it is leaving, you have to take it as a minus. Current when it is leaving, you have to take it as a minus. Okay, now come here. So here you have one more. Here, from this node, this current is leaving, but here one more current is leaving in between, that is minus 1.3. And this I is also leaving from the node, so minus I with equal to what you have to write, algebraic sum of currents is 0. So this is according to the statement of Kirchhoff's current law or Kirchhoff's first law. So by this you can find the value of current I na. How means 2 plus 2 4 minus 1 3, 3 minus 1.3, 2.7 minus I equal to 0. Yes or no? 1.7. So I is equal to minus 1.7. So simple examples you can find. Simple examples you can find by applying Kirchhoff's laws to the simple circuits. So this is about Kirchhoff's first law. Similarly, I am considering one simple circuit to understand Kirchhoff's second law or Kirchhoff's voltage law. So for Kirchhoff's voltage law, what you have to consider? You have to consider a closed loop. Okay. So I am drawing a closed loop with the points A, B, C, D. So from the point A, I am having one resistor with the resistance 2 ohm. Okay, so this is the point B, and here I have one cell with the EMF 1.5 volt, and the point C, and here I have one more resistor with the resistance 3 ohm and the point D, and this we have to close again. So here consider one more EMF or cell with the EMF 3 volt. Okay, isn't it a closed circuit? So for this, can you apply Kirchhoff's voltage law? Kirchhoff's voltage law says that the algebraic sum of EMFs is equal to algebraic sum of IR products. Okay, so now start from this point. So and current also we have to show na. So consider that I1 is a current in this way, and here we have a current as I2. And let move in a clockwise direction. So when you are moving in a clockwise direction, start from A. So same direction. The direction of traverse and direction of current is same. So it is plus 2 I1 IR. I1R. Okay, let come here. We don't have any IR here. Again here we have IR, the same direction, plus 3 I2. So this is what the algebraic sum of IR products. So now again start, and here also we don't have any IR products. Okay, on the RHS we will be having sum of EMFs. So here come here. So it is from positive to negative. So if the EMF is from positive terminal to negative terminal, we have to take it as a minus 1.5. Again come here, we don't have any cell here. Again here we have negative to positive. Negative to positive means plus 3 we will be having. Okay, so what you get here? So see here, whatever the current moving here, I1 for the 2 ohm, that can be taken equal to the current moving in 3 ohm, because in a single circuit we are having. So we can take it as a I1 I2 equal to I1 is equal to I2 equal to I. Common current moving in this circuit is I, you can take. So 2 plus 2I plus 3I is 5I, and 3 minus 1.5 is 1.5, and you can get the value of I as 1.5 divided by 3. So by this simple circuit, by applying KVL, Kirchhoff's voltage law, you can find the amount of current in this circuit as 1.5 divided by 3. Okay, these were the simple exercises I have told you to understand the laws perfectly. Okay, so while solving the problems, you have to make use of both the laws in a wide pattern. Okay, so these were about Kirchhoff's first law and Kirchhoff's second law. Okay, so now moving on to the next things, we are having after the Kirchhoff's laws, we are having 3 important electrical circuits there: Wheatstone's bridge, meter bridge, and potentiometer. Okay, so for the first, we will discuss about Wheatstone's bridge. So what is this Wheatstone's bridge means? the new name you are hearing. So Wheatstone's bridge is nothing but what? It is one electrical circuit. It is one complicated electrical circuit where we are having 4 resistors. Let's consider PQRS. So 4 resistors are connected in a quadrilateral pattern. So among them PQR are known to us. If PQR are known to us, we can find S. Or if PRS are known to us, we can find Q. Okay, so this Wheatstone's bridge is used to find one unknown resistor with respect to 3 known resistors. Or you can say that this Wheatstone's bridge is also used to compare the resistances of the resistor. Okay, so this Wheatstone's bridge is devised by the British physicist Sir Charles F. Wheatstone in the year 1843. So that's why the name Wheatstone's bridge. Here the 4 resistors are designed in a bridge pattern or in a network pattern. That's why it is also called as Wheatstone's bridge or Wheatstone's network. Okay, this is devised by Charles Wheatstone in the 1843. That's why the name Wheatstone. Okay, so how the Wheatstone's bridge will be, just I'll show you first. Consider that you are having 4 resistors PQRS and they are connected in a quadrilateral pattern like this. Means if A, B, C, D are the 4 points of a quadrilateral, the resistors are divided like this PQRS. Okay, let's draw the diagram first, then only you will get a clear idea. Okay, so let's consider a point A. From point A you are having one resistor, then B, one more resistor, then you are having C, one more resistor. Here you are having one point D, and between D and C you are having one more resistor, and between A and D you are having one more resistor. So this is a diagram of Wheatstone's network. Diagram of Wheatstone's network where 4 resistors are combined in a quadrilateral pattern. Okay, and between these points B and D we will be connecting one galvanometer. Galvanometer means this is also one electrical device which is used to find small currents. Okay, so this is how the resistors are designed. Let's call this as P, Q, R and S. 4 resistors are connected in a network pattern or in a bridge pattern within the points A, B, C, D. And here we are having one cell and one key. So this is how the Wheatstone's bridge is designed. So this is a electrical circuit in which 4 resistors are connected in a bridge pattern or in a network pattern, by using which we can find one unknown resistor with respect to 3 known resistors. Or this Wheatstone's bridge is used to compare the resistances of the resistors. Okay, so by using this, here we can see that here we are applying one cell with the EMF E and one galvanometer. Okay, so this is how Wheatstone's bridge is constructed. This is the construction of the Wheatstone's bridge. Okay, now let's think about what is the principle on which Wheatstone bridge works. What is the principle behind Wheatstone bridge works? Okay, so in this we are having galvanometer. Galvanometer is showing you small currents. Galvanometer is a device which gives you small currents. Okay, now we have to adjust the resistance in this network such that the current in the galvanometer is 0. Current in a galvanometer, let's consider this as IG. Ig. The current in the galvanometer is Ig. Like this I have written. So that current, we have to apply the resistance in such a manner that current in the galvanometer is 0. Means Ig equal to 0. So if Ig equal to 0, at that time the potential difference at B and D will be same. The V at B and D is same. That's why this whole network is electrically balanced. This is the principle of Wheatstone's bridge. Means the principle of Wheatstone's bridge is, we have to, when we apply a resistance in such a manner that the galvanometer current equals to 0, at that time the voltage at B and D will be same. Hence the whole network will be electrically balanced. This is the principle on which Wheatstone's bridge works. Okay. So now, what is the proof for this principle that we have to derive? Proof of the principle that we have to derive. Okay. Before going to that, now let think of what are the amounts of current moving at this PQRS. Okay. Now let's consider I1 is the current moving in R and I2 is the current moving at P. I1 current is moving here, I2 is moving here. So this I2 goes like this, but here one more current Ig is divided na. So next in the Q, what is the amount of current? I2, the same current came, but Ig is subtracted. That's why I2 minus Ig. The current in Q is I2 minus Ig. But here you come I1 and the Ig is added over here. So the current in S is what? I1 plus Ig. So in R we have I1, P, I2, Q, I2 minus Ig, D, S, I1 plus Ig. Okay. So now, to prove the Wheatstone's bridge, to prove the condition of balance, we have to consider that in this closed path A, B, D, A. In the closed path A, B, D, A, you just go on writing the derivation. Let apply KVL, Kirchhoff's voltage law. Let apply here. So here we have I2P, means the direction is like this only. The traverse is like this, plus I2P. Here what we have? I2P. Come here. IgG. So G is what? Resistance in the galvanometer, plus IgG. Okay. Again come here. Like this you go. The direction of current is opposite to the direction of traverse. That's why minus I1 R equal to 0. This is by applying KVL to this loop. Okay. So here by the principle you know that we have adjusted the resistance in this circuit such that the Ig, the current in the galvanometer is what? 0. So if it is 0, this whole term vanishes. So what we have here? I2P minus I1 R equal to 0. Or also you can write it as I2P equal to I1 R. And then what is I1 divided by I2 by that? I1 divided by I2 is nothing but what? Or also you can take I2 divided by I1. I2 divided by I1. No, I1, I2 only you take. Is P by R. I1 divided by I2 is what? P divided by R. Call this as equation number 1. Okay. Similarly, to this closed loop, what? B, C, D, B. You apply KVL again in the clockwise direction. The closed loop B, C, D, B. In the closed loop B, C, D, B. I am applying KVL, Kirchhoff's voltage law. Let's start. B, C. what is the current? I2 minus Ig into Q. What is current over there? I2 minus Ig into Q. And here you don't have any EMF, so that is not a matter. You can directly take it equal to 0. Okay. Next, here I1 plus Ig into S, but the direction of traverse is like this, current is like this, so you can take it as a negative. So I will write that here only for the understanding. In the circuit BCDB we have plus I2 minus Ig into Q and minus I1 plus Ig into S and again minus Ig into G equal to 0, and by the principle Ig equal to 0. So here what you will get? I2Q minus I1 into S. IGS is 0, Ig is 0. So you have I2Q is equal to I1S. I2 by Q is equal to I1S. So similarly, I2 divided by I1 divided by I2. What I1 divided by I2 gives? I1 divided by I2 gives Q by S. Call this as equation number 2. So by comparing the equation 1 and 2, can you write P by R is equal to Q by S. So this is the equation of Wheatstone's bridge. Means in this, if you know P, R and Q, you can find S. If you know P, R and S, you can find Q, like that. Okay. So this is the condition of balancing Wheatstone's bridge. This we have proved by considering this construction. Okay. So this is used to find the one unknown resistor if three are known for us. Okay. So in the next class we will discuss about meter bridge and potentiometer. Okay. In the next class I'll finish up the unit current electricity. After that we have to go for the important part of the current electricity, that is numericals, which are very important in physics. So as soon as possible you try to be perfect in all the things which I have taught up to now in the current electricity, because to solve the problems you have to be perfect in the theory. Okay, try to make the list of formulas to solve the problems. Okay, so today's class I'll finish up with this. Thank you.